Okay, thank you, Herb. This is a hard act to follow. I'm going to tell you about our work on graphene, and I changed the title a little bit. I'm going to focus just on the STM work because I know Ginny Lau is going to talk about the transport later on. So first of all, I want to thank my friends and colleagues who helped me get ready for this. Nancy Sandler, Michael Führer, Maria Vozmediana, and Leonid Levitov. I'm going to start by telling you a little bit about making graphene. I actually have a movie of how we make it in our lab. And I'm going to pass around a piece of it. Then I'm going to tell you about physical properties, many of which you've already heard about. And then I'm going to tell you about our own experiments, how we actually look at it and look at the individual atoms. So let's start here. So carbon, we have the fourth column of the periodic table, and today we're going to talk about carbon. But what all these atoms have in common, they have 4 valence electrons in their outer shell. Now, carbon can make 2 types of chemical bonds. Those 4 orbits hybridize to form either an sp3 bond, which is a tetragon, which is symmetric in space, and this form of carbon, which forms diamond, has been known for a long time. And the other form, so we've known about it. It's written in the old Indian Vedas. It was found on the banks of the Ganges in India. And the second form, which is graphite, took much longer to discover, at least to be recognized. So it took another 5.5 millennia to find the second form of carbon, which is graphite, and it took only a few years to go from that to the pencil. So in fact, you have graphite in each one of the pencils, although some of you still call it lead. And do you know why that is? It is because in those days, there's this black stuff that is soft and it leaves this mark. People thought it was lead. And it took another 200 or 300 years for the chemists to figure out that actually it's carbon and not lead. Now, what is interesting about carbon, and this is special because it's the first one in the column, is that the sp3 bond is not the stable one. It is the sp2 that's the stable one. For silicon, and that goes back to the question about the silicium, it's the sp3 form that is stable, and we have to work hard to make the sp2 form stable. So eventually, this is what happens. And this nice diamond goes into graphite. Now Andrei Geim told you about the molecule. So the sp2 form of bonding happens in benzene molecules, and you have, so each carbon is bound to its nearest neighbor by this sp2 bond, and you have in the plane, the bonds are 120 degrees apart, and the 4th electron sticks out of the plane and it's responsible for electronic properties. So the benzene ring, you have each carbon is connected to 2 nearest neighbor, and the 3rd bond goes to a hydrogen. Now imagine snipping off those hydrogen bonds and replacing them with another carbon. And then you can tile space. It can just go forever. And this is what we call graphene. So to reiterate, these sigma bonds are responsible, they're flat, they're 120 degrees apart, so they're responsible for the crystallographic structure, for the 6-fold, for this honeycomb structure here, and they're cause the stiffness and the flatness of the material, which we've heard about. They are the strongest bonds in nature, and this is why graphene is so strong. And the pi orbitals are responsible for the electronic property. These electrons can walk around on this lattice and do all the wonderful things that we hear about. So now this graphene sheet is the mother of all graphitic allotropes. The 3-dimensional form is you just take the graphite sheets and stack them up and you get graphite. And then more recently, and it took another few hundred years to discover the low-dimensional form, the zero-dimensional buckyball, which is basically taking graphene and folding and crumpling it up into a ball, was discovered in the 80s. And the one-dimensional form took another 10 years. So you take the sheet and you roll it up in a cigar, and you get a carbon nanotube. So why did it take so long from graphite to these low-dimensional forms? It is not because they don't exist in nature. Soot that comes out of your car, any pollution, has these tiny particles around, except that in order to be aware of it, you had to develop the experimental tools, the microscopic tools, to see these things. So these three materials exist in nature, and now we are going to the two-dimensional material, which was discovered another 10 years later. But the difference between the two-dimensional, the graphene, and the other ones, there's a fundamental difference between them. The 0D, 1D, and 3D exist in nature, whereas the 2D cannot exist. And we know that, at least we thought we knew that for a long time. So instead of trying to make it in the lab, people tried to make toy models out of it. So graphene existed, but as a theoretical model. That graphene was actually invented back in the 40s by Russell Wallace, who was working for the Nuclear Commission in Canada, and he was assigned right after World War II. And he was assigned the task to figure out the band structure of graphite. He tried it, and it was just too complicated. So he decided to simplify it. Let's take just one sheet and calculate the electronic properties, and that worked. So that was a toy model that was once and again pulled out of the drawer and dusted off and used for all sorts of exotic things like diamagnetism in graphite. It was used by high-energy theorists. Gordon Semeneff and Duncan Haldane used it for something even more exotic, having quantum Hall effect without magnetic field. But nobody thought that one day this material will actually become a reality. So this is why when this actually happened in 2005, people were very surprised. And the reason for that is, Andrei Geim already showed you the movie, there is no long-range order in 2 dimensions. We cannot have crystals, we cannot have superconductivity, and there is a famous theorem by Merman and Wagner that tell us that, and we should all obey it. So as Andrei Geim told you, can we get around it? And the way to get around it is illustrated here. 2-dimensional material is perfectly stable as part of a stacked material like graphite. So can we just cheat nature? Can we get around this problem and just pull out a layer? And Andrei told you that this is exactly what they did with the scotch tape. And I'm going to show you how we do it in the lab. And this is a movie that was prepared by Barbaros Ozilmas.
Take a scotch tape and gently lay it down on a flat surface. Next, take clean metal tweezers and pick a thin graphite flake, and then place this gently onto the scotch tape. Next, fold the scotch tape at the edge of the graphite flake. Peel it off gently, and do this step several times until you obtain a nearly transparent region on the scotch tape. After this, take a clean silicon wafer to transfer the scotch tape graphene onto the wafer. Use plastic tweezers and gently rub the area of the scotch tape where graphene may potentially be. Slowly peel off the scotch tape so as not to break any potential graphene sheets. Use an optical microscope to view and find graphene. Graphene appears as a purple spot on the screen. At the center of the screen is multi-layer graphene, and at the right corner, lower right corner of the screen is single-layer graphene.
So this is how we make it. In fact, I prepared, and you already heard that one can see it because it absorbs 2.8% of the light. So I prepared some graphene on a glass slide. Now this is not done with this way, with this method, because the flakes are too tiny to see. This was prepared by chemical vapor deposition, and I'm going to pass it around so you can see what it looks like. Now to see it under a microscope. Everybody says, oh, how easy it is to make graphene. All you need is scotch tape and a piece of graphite or a pencil. In fact, the next step to find it and to see it is where you need the $1 million lab. You need this. So some of the properties of graphene. Let me start with mechanical properties. This is a graphene bubble that was blown up in Paul McEwen's lab. So there is a pressure. There's 1 atmosphere differential pressure on this graphene, 1 atom graphene sheet, and it blows up. And from the curvature here, you can figure out 2 things. First, you can measure the strength of the material, and when you go to Google, you can find a table like this. For example, steel would be here, various ceramics are here. Graphene is literally off the chart, and that is because those sigma bonds. Another very useful property is that it's completely impermeable because those carbon atoms are very close. So this group, they had a one atmospheric pressure differential on this bubble, and for about a week nothing came out. So it leaked out slowly over a week, but it leaked out from the edges. No, okay, even though helium is such a small atom. Thermal properties, it has huge thermal conductivity, which is potentially very useful in electronics, and that's again because of those strong sigma bonds. So the conductivity of graphene is about 5 times larger than diamond and about 20 times larger than copper. Chemical properties are again amazing, and people have shown that one can detect single molecules of ammonia and carbon oxide, and so one can make extremely sensitive detectors. It's a very sensitive nose. So 1 atom added to this sheet gives you a jump in resistivity of about 1 ohm or 2. And you can actually watch the atoms being deposited. This was done by the Manchester group. The optical properties, so you heard already about this, and you're going to look at the graphene when it gets to you. It absorbs 2.8%, so in principle, when you look at it against the light, you should be able to see that shadow. So we have, it is conductive, it has a very good conductivity, it is transparent, so one can imagine using it for your LCD screen and your phones, and already Samsung Electronics, who is at the frontier of this research, has promised us a flexible touchscreen this year. And by now I believe them. Because they promised us large sheets of graphene when I was at a conference in the summer of 2009 in Korea, at a time when our samples were never larger than a few microns. And I said, oh, I don't believe a word. And by Christmas, they did have large sheets. So maybe this will come true. There are many, many applications. They are ultra-fast transistors. There's a 100 gigahertz transistor from IBM here. And one of the most exciting that is just beginning to come online is biographene. It turns out because the graphene is all carbon, all organic molecules, all organic material just loves graphene. So neurons just love to go on graphene. You see neurons on graphene versus neuron on a regular cover grass. They just grow there. And there have been very interesting experiments. DNA that sits on graphene is protected from breakdown by enzymes. So you can actually hold a single strand there for about half an hour and imagine doing things like injecting it into the body for medical reasons, for gene therapy or whatever. One can build a scaffold for differentiation of stem cells and into bone and neural cells. That has already been demonstrated. And one of the other very exciting prospects which we started working on is trying to use it for DNA sequencing, for fast and efficient and cheap DNA sequencing. So there are many applications that one expects to come online. Some of them will actually happen, some not. Okay, if you go on the web, you see things like this. So have we reached the Carbon Age? And you see one long-standing criterion is the physical material with which most technologies of an era are manufactured. And now it looks like we're going to graphene. This is a blogger, Keith Wiley. We'll see about that. So let me talk about electrons in materials. So electrons in a material share something in common with marbles in a jar. So let's say that you can add your electrons. So the first ones will go to the bottom, and you keep throwing electrons in. When you finish the first row, they go to the second row, and so on and so forth. And when you shake it, they get into the empty spaces. And the fuller it is, the ones at the bottom are more inert. They just don't do anything. They're dead. The only ones that do anything are the ones that are at the top. So we call that the Fermi energy. And those are the only ones that interest us. Those are the ones that contribute to conductivity, to the electrical property, to the optical properties, to the thermal properties. And all the others are kind of dead, uninteresting. The shape of the jar is determined by what material you work on, by the atoms that the material is made of, by the crystallographic structure. And once you finish filling up your jar, you close it, and the next electron has to go to a second jar. So this is illustrated here. So this is a valence band where nothing happens. The second jar you start filling. When it's half filled, your Fermi energy is out here, and the top electrons can move. There's still room for them to go somewhere. So this would be a conductor. An insulator will look like this. When your Fermi energy, when you just fill the jar and you don't have enough electrons to fill the second one, enough energy to go to the second one, this will be an insulator because the electrons at the top can't move. Now, usually the shape of the jar and where the Fermi energy is dictated by God or by our local chemist. In graphene, as you will see, this is a little bit different. So in a normal metal, like copper or take gold, if I plot the dispersion, the energy versus momentum, this looks classical. It's parabolic. So the energy of the electron versus its momentum is a parabola, and we can take out the prefactor, we call it a mass. Although it usually doesn't have anything to do with the actual mass of the electron. How is graphene different? Now, graphene is different because of its honeycomb structure. So when you throw electrons in there, they refract very strongly from the lattice. So instead of having such a nice, beautiful parabola, you get something that looks like this. And the Fermi energy that sits right here, you see this material can't make up its mind if it's a conductor or an insulator. In the middle here, it's an insulator. The Fermi energy is in a big gap. But on these 6 points, it's a conductor because the conduction and valence band touch there. So there are 3 ingredients that go into the spectacular electronic properties of graphene. And those are the fact that it's 2-dimensional, the fact that the structure is honeycomb. and the fact that all atoms in it are identical. Now, look, have I said carbon anywhere? No, it doesn't have to be carbon. In fact, you can make graphene out of anything. I had a demo here, but it's gone. So people are trying to achieve the same electronic property using cold atoms, for example, or doing something with, or moving atoms on the surface of copper and making honeycomb structures. So the fact that it's carbon doesn't enter here. But where it does enter is that it's the only material in nature that we know of that is stable in this form. So if you go down the fourth column, nothing forms a stable sp2 bond. So that's why this is the only material we have to work with here. Now, if we zoom into one of those corners, the band structure looks nicely conical, and the bottom here we have the so-called holes, negative charged particles, and the conduction band here touches the valence band. And the dispersion looks like this. The energy is linear in momentum. Remember, in the normal material, it is quadratic. Now, what does it mean? Let me remind you something. This means that the mass of this particle is 0. And the Fermi velocity here, Vf, which is just the slope, is 10 to the 6 meters per second, which is 1 over 300 the speed of light. Now let me remind you a little bit, this is the mother equation of special relativity. Now most of you would be familiar, most of your students would be familiar with this. When the P here is E is the energy, P the momentum, M the mass, and C is the speed of light. Now when the particle is at rest, when the momentum is 0, we recover the T-shirt formula. Now, what happens when the mass is 0? When the particle has 0 mass, like photons and neutrinos, the energy is linear in momentum, and the proportionality factor here is the speed of light, and this is how photons move, for example. These are ultra-relativistic particles. They have to move at the speed c. They can't help it. You can't accelerate them or slow them down. And this is exactly what graphene is, except that we have a different speed of light. And we can actually tweak the speed of light, as you've heard in Andrei Geim's talk. So the electrons in graphene are ultra-relativistic particles. And we call them massless Dirac fermions because you can't put two of them in the same place. You stack them up like marbles, MLDs. Okay, so one of the properties of these electrons is chirality. Now, normal electrons, so this is this car. When you come to a wall, they know how to make a U-turn. Okay, and they actually don't burn. They are reflected. And now look what happens to this guy. These guys, they're chiral. That means they don't know how to make U-turns. So they either go through the wall or go around it. There's no choice. So this is what gives it the very different electronic properties. They are faster than normal electrons. They go through any barriers, and you just can't stop them. So here's the band structure. One of the things that we are very interested in and we can measure in STM is what's called the density of states, which is the number of marbles you can put in at a given energy. Basically, this density of states as a function of energy tells you the shape of the jar. Now, in normal graphene, when you don't do anything to it, the Fermi energy is right here. So basically, we filled this valence band, and we haven't started filling the conduction band, and we have 0 electrons. As I said, it should be an insulator, but there's nothing stopping an electron from going up here. So therefore, this is a very special point called the Dirac point. Now, what is remarkable about this is that because there are no electrons here, I can put my graphene as an electrode in a capacitor and just apply a voltage between it and the ground, and it allows me to walk up this energy here. So I can basically I can change where I sit here on the so I can change the number of electrons that I have very easily. So I can, with just a battery, I can change the resistivity of this material. So as you go down the line here, when you come up here, the resistivity is going to become very high, like a few hundred about 17 kilo ohms theoretically, but it's never going to be infinite because you can't stop them. You cannot make it into an insulator. So what happens when you apply a magnetic field, and we do this? Let me go back here. You apply a magnetic field. So classically, this is what you would draw it like. Now, when you have a magnetic field and two-dimensional electrons, this field, you can think of it as breaking up into these tiny quantum flux lines. And these flux lines are, so each one is like a tiny solenoid, and each electron will have an orbit to move around these. So you see, if you have a sheet of graphene or anything else, of two-dimensional electrons, you apply a magnetic field, and each one is going to have its own little orbit to orbit around. And I'm going to start throwing an electron into this jar. Oops. Okay, and fill them up. Now, the next electron has nowhere to go to. So it has to but it still is required to sit on one of those flux lines. So it has to go up to a higher energy. I illustrated this by making a loop here. And these things are called Landau levels. So when I apply a magnetic field, this band structure is completely changed, completely different. It breaks up into these Landau levels. We still have one at zero energy here. And the density of state, my jar, develops these ears. So here at zero energy, I have room for a lot of electrons, but when I go to the next one, it becomes an insulator. And this causes what we know as the quantum Hall effect. You'll hear more about this later, so I'm going to move on. Now, so these Landau levels, so if you ask, is there a smoking gun for these for the relativistic electrons, for the massless Dirac fermions, and there is. And these are the Landau levels. If you go to a normal two-dimensional system, the Landau levels look like equally spaced. There is nothing at zero energy, whereas in the ultra-relativistic, Dirac fermions are going to have a spectrum like this. So it's very easy to tell where you are. So essentially, if you have a tool that can measure the density of states, then you can tell whether you have ultra-relativistic Dirac fermion. And one way to do this is to look at it with a scanning tunneling microscope. So a scanning tunneling microscope is, let's say that we have a material, and you bring to it a sharp tip, and you try to pass a current through it. This is a zoom into the tip. The last atom in the tip is this one here, is the closest to the other atoms on the surface. And then, just like in a record player, you move your tip along this surface, and you can have a control system that makes sure that the current is constant, so then it'll measure the height of the surface. So it'll measure you'll be able to see the position of each atom. This is called topography. On the other hand, so this is a little bit like an old-fashioned record player where you have a needle going over the grooves, and then you have a servo system that registers the height of each groove and the time sequence, and it transforms it into a sound. So what we do here, we transform these movement of the tip into these bumps. Now, I should say that if my tip was sitting right on the surface, it'll be a short. So I wouldn't be able to tell what's going on. If the tip is too far from the surface, nothing is happening. There's no current. So you have to be close but not touching, and this is called a tunneling regime. And I have a little movie here that illustrates what tunneling is, and this is a little bit like the car going through the barrier. Okay.
Some of us were taught in high school that the electron orbits around the nucleus, like a planet around the sun. However, this description has been understood as a gross misrepresentation for the better part of the last century. As it turns out, there is a characteristic uncertainty related to the very small. No one can tell exactly where something is. The best one can do is figure out where something is most likely to be. We can visualize this with something called a probability cloud. Here, we see the probability cloud of a proton at the center of a hydrogen atom. The denser regions are where the proton is more likely to be found. However, this uncertainty is not due to an inability of ours to measure the small in an exact manner. It is a fundamental aspect of the world in which we live, and its implications are extraordinary. Let us take, for example, the phenomenon of tunneling. If we can't tell exactly where something is, then it follows that we can't tell exactly where it's been, or where it will be. The best we can hope for is where it most probably will be. So there's a small chance that a racquetball thrown repeatedly at a barrier could just tunnel through the barrier, appearing almost magically on the other side. We don't see this often because a racquetball is pretty big, and its uncertainty pretty small. But if we deal with matter on the subatomic scale, it becomes much more likely. Here our projectile approaches the barrier. We see here its probability cloud. Although it's most likely near the center of the cloud, we can see that there is a small chance of it being on the other side of the barrier. And so, sometimes, it is. Tunneling isn't a mathematical trick or an assumption. It's an observable fact. It's made use of commonly in modern electronics, and in a real way allows for life on Earth. To see why, let us trace the creation of a photon in the sun. The light from the sun that we see reflected off the moon, the light which drives the Earth's weather, that provides the energy for life, all originates from the process of nuclear fusion in the sun. Two light atomic nuclei collide, forming a new element, and in the process, light is released. But these nuclei are both positively charged and so repel each other. Only if they have enough energy can they overcome this potential barrier and fuse. But if you do the math, the nuclei in the sun don't have enough energy. The sun's just not hot enough. Nonetheless, the sun shines. And it does so because of tunneling. Just like our physical barrier, there's a chance that our particles could be on the other side. And so, the sun shines.
Okay, so this is the process that we use in our tunneling microscope. So so when you are close enough, it's enough to move, and you measure a certain current. It's enough to move one atom away, and the current will be reduced by a factor of 1,000. So it's an extremely sensitive technique to look at surfaces. And so we can measure topography, and we can measure the electronic density of, say, the shape of the jar. And this is our group. This is a home-built STM, which didn't cost that much because we built it ourselves, but it cost us about 2 years of work. And these are all the pieces, and here this is what it looks like when they're finally put together. So it goes down to low temperatures, to 2 Kelvin. We can put on a magnetic field up to 15 Tesla. And what is very neat and lucky about this is that we have a coarse motor that allows us to scan large area, large, like a millimeter, and we can zoom into subatomic resolution with a fine motor. This microscope was built to look at something that now may seem boring to you. It's vortices in superconductors, to look at the dynamics of vortices. Everybody who ever built an STM knows that when you finish building it, the first thing that you do, you put in a piece of graphite, because we know the distances between atoms. We can calibrate the motion of our tip. So that's what we did. And this is what we saw. This is a piece of, and we actually, so we didn't go to the fancy graphite that people usually put in there. We are too cheap to buy the $3,000 piece of graphite. So we bought a $20 piece of graphite that is very flaky. And this is what it looks like. And here I'm showing you a mesa here of one of these flakes. And we zoomed in and we saw this. Now this really puzzled us because graphite doesn't look like this in STM. It actually looks like this. We only can see every other atom because of the stacking. So this was the first puzzle. Then we went and did the spectroscopy, density of states. And density of state looked like this. It's linear and vanishes here at this point. This is where the Fermi energy is at the zero. Again, this is not what you're supposed to see on graphite. Graphite, the density of state doesn't vanish anywhere. And then we were going to test our magnetic field. So everything was wrong here. Then we went to test our magnetic field, and we saw these things, these huge peaks, instead of seeing something like this. So we knew that something is wrong, and we scratched our head. And then I remembered, this was in 2006. This was in the summer of 2006. I remember that in March, I went to the March meeting that year. This is the huge meeting of the American Physical Society that deals mostly with condensed matter physics. And I like to go to talks that are out of my field. And I and 9 other people attended this talk. And I remembered something about these Landau levels being weird, because normally I was used to working with non-relativistic electrons. Landau levels should be equally spaced. And then I remembered that it goes differently for graphene because of this conical dispersion. So we went back and checked it, and sure enough, this linear dispersion is nothing but what you expect for graphene, and these are the Landau levels that are right on that you expect for graphene. So then we stopped working on vortices. So one can observe it. Another surprise was we looked at these mesas here, and we went into atomic resolution. So we continued looking at the surface of graphite, and we saw this beautiful pattern here, but it was all wrong. Instead of the distance between these atoms being of the order of a fraction of a nanometer, this period is much larger. And then when you zoom in, you actually end up seeing the atoms. So it looked like we have something like a rotation, but we had no idea why that is. And then we saw that if we get off this step here, we see the normal behavior. We see the atomic resolution. So what is going on here? And I'm going to show you an illustration. So we figured out eventually that what we're looking at is Moiré patterns. And let me tell you what Moiré patterns are. And you probably have seen it a million times. Let's say that you take 2 patterns. So this is one pattern here. It is maybe too fine to see. And take another identical pattern and put it on top of it. And now, depending on how their relative rotation, you can develop a superstructure. It is called a Moiré pattern. The larger the angle of rotation is, the smaller the super pattern is. And once you get to a certain degree, here is in this case it would be 60 degrees, again, it repeats itself. Okay, so you get this huge pattern when you have a small angle of rotation, a tiny pattern when you rotate away from alignment. And so this is what is actually going on here. So what we saw is these Moiré patterns because we had a top layer. We had a top layer and 10 degrees, 6 degrees, and you see the pattern grow here. And the super period is roughly inversely proportional to the sine of the angular rotation. It's very easy to calculate. It's kind of simple geometry. And then we looked at the spectroscopy. So when we are off the pattern, it doesn't look very pretty, but it's still along of what we expect for graphite. And we go on the pattern, and there's a dramatic change in the density of state. So it's as if just by the rotation we change the shape of the jar. So in fact, just by a simple rotation, we can change the density of state, the band structure of a material. Something that up until now we could only do with the help of our chemist friends. So no matter where you go, on the rotated area, you have these two peaks. And having peaks in the density of state is very important, because if you put your Fermi energy inside one of the peaks, sometimes really surprising things can happen, like superconductivity, like charge density waves, all sorts of neat things. So it's really nice to have something like this that is so easy to manipulate. And here we did all sorts of various angles of rotation, and we see that the distance between these peaks is proportional, almost proportional to the angle of rotation. So the larger the rotation, the further apart in energy the peaks are. What is going on, if you look at these Dirac points, the 6 Dirac cones in the 2 layers, red is the top layer and green is the bottom layer. When you have a rotation between them, the Dirac points are rotated relative to each other, and when they meet here at this positive and negative energy points, and you can imagine immediately that the larger the angle of rotation, the higher in energy you'll have to go to see them meeting. And when they meet, the bands hybridize, and you form these peaks. They're so-called Van Hove singularities. So we can do this just by a simple rotation, and we find it quite amazing. Finally, and this is my last slide, we can use our STM to image the electronic wave function in the material. Now, as we go through these Landau levels, when we are sitting inside a peak where we have a large density of state, the wave function is extended. So the electron is spread over the entire sample. Of course, it's not perfect because there are impurities. So when we are sitting in between Landau levels, the wave function is, you just have a few available states, and they'll just sit on those impurities. So you can see the impurity right here. Right now it's sitting on an impurity. Now when I go inside a Landau level, it's spread out and it's extended. Just like what theorists told us. We don't always like to prove them right, but here it is. They certainly are. And here's the summary. I have to thank my group, and here are their pictures. And this is a list of my collaborators, both theory and experiment. So what I showed you is that when you put graphene on graphite, lots of interesting and fun things can happen, and surprising things can happen. And our second surprise was what happens when you twist layers of graphene. And the outlook for this field is just limitless, and you've heard a lot from Andrei. What we in the lab are thinking about, graphene does everything. Can we make it superconducting? So this is one of the questions that were discussed at this conference. Can we make it magnetic? Can we have, I haven't told you anything about the spins because there still is not very much to tell about it, but can we make a pure spin transport in graphene? And there are lots of people who are working on this, and we've heard very nice talk about this at this conference. And finally, and I'm very excited about potential biological application. And in fact, I'm most excited about the things that are not on this list, which we hope to see. Thank you very much for your attention.
Okay, so the floor is open for questions and comments.
This is a very basic question, and it goes back to the first talk also, but we're saying that this is two-dimensional, and if the atom has a thickness, then doesn't that, I just know my students are going to ask me, how is it two-dimensional when there's a thickness to the atom?
So this is this is a very good question. How come why do we call it two-dimensional? And in fact, we live in a three-dimensional world. And I think we should say it's as two-dimensional as you can get in our world. And we can measure how thick it is. It's about 0.3 nanometer thick. And this is the extent of the pi orbitals out of the layer. So two-dimensional just because that dimension is much, much smaller than the other dimension. So in that sense, two-dimensional. So, I mean, in principle, you could call a piece of paper two-dimensional, right? Because we usually loosely do. But in fact, with this two-dimensional piece of paper, you're going to have to cut it how many times to get down to the thickness of graphene? Any guesses? Many. Yeah, it's many. It's about 1 million. Okay, so in that sense, it's two-dimensional.
Go ahead.
Yes, graphene has different characteristics. In one instance, you indicated that it can be a conductor. In another instance, it can be an insulator. How do you control what it's going to be?
Okay, it is never an insulator, and this might be a problem. Now, the way you control it, I didn't show this, but I hope that Jeannie is going to show it. Imagine, okay, this is your electrode, a piece of metal. This is graphene here, okay? And now I'm connecting a battery. And this is called gating, and I'm changing the voltage. Now, you know, when you connect a battery to a capacitor, when you charge it, you have a certain amount of charge on the bottom electrode, and the amount of charge on the top electrode has to match it. Okay? Now, in normal metals, there are so many electrons already in the material. You have a flat jar, so that adding a few doesn't make any difference. But in graphene, when you sit at the Dirac point, where there's 0 electron, density of the state is 0, any electron that you add is going to change the energy. So you're going from 0 electrons in the jar to a finite number, which increases increases monotonically with the gate voltage that you apply, and you make it more conducting or more insulating, or never absolutely insulating. When you sit at the Dirac point, the resistivity is about 10 or 17 kilo ohm, depending on how good your sample is. And the reason is because of this chirality, because we can't stop them. Even though there's no electron in there already, when you shoot an electron in, it just goes through and you have a current because of this chirality property.
How are you controlling the electrons? Are you...
I'm changing the voltage on the battery. That's it. You just control the number of electrons, and then if you want, so that determines how many you have in your sample. But then you connect 2 leads to the graphene itself. Now it's longitudinal, so source, drain, and you can push them through. Okay? So in a sense, you have a bottom gate that determines how many electrons you have in the material, and then you can shoot them through by the source-drain voltage difference. So that determines the current. You measure the current, and from that you can get the resistivity.
When you were showing the picture with the magnetic field, what happens if you rotate the magnetic field 90 degrees? How does that change what you see?
So that's a very good question, and people are doing these kinds of experiments. So so as I said, you have when magnetic field is perpendicular to an electron, it has this cyclotron orbit. Okay. Now, when the field is parallel to the layer, the only time it's going to make a difference is when you can make cyclotron orbit. Now, the orbit of the cyclotron orbit is something that goes like a square, inverse square of the magnetic field. So you have to have a huge magnetic field for your orbit to fit inside this two-dimensional layer. We don't get there. So when you tilt it away, it's only the perpendicular component that makes a difference. The parallel component will not affect the orbital motion. However, there's something called Zeeman splitting, which you probably know about, splitting because of the spins. And there, it doesn't matter if the field is parallel or perpendicular, that splitting is going to be there regardless.
Oh, that's loud. When you were just talking about gate voltage, does that mean you can make a transistor out of just a single piece of graphene with no doping or no messing about?
Absolutely, and this is, I showed you the IBM. So first of all, you can make what's called a field effect transistor, so where you change the resistivity with just the gate. And this was done by the IBM group, and that's the 100 gigahertz transistor. One of the things about the semiconductor industry, you want to be able to turn completely off. You want to have an insulating state, an on-off. So it's very important to have a large on-off ratio. And just because of the chirality of the electrons in graphene, I just told you can't turn it off. So that's a big problem. So people are working hard to figure out how to open a gap in the graphene. Well, all these wonderful properties about the Dirac point. One of the properties is that you can never turn it off. Even if you're at zero at the Dirac point, you can always get the electrons through. So you have to open a real band gap in your jar there, right? So people are working on that, and one way to do it is to make thin strips of graphene. But Jeannie Lau is going to tell you much more about her efforts in that direction. Yes, people who are thinking of using it in electronics have to solve the gap problem.
When you showed the Moiré patterns from the two-dimensional graphite, how do you control the angles? Or is that just by chance that you find a couple of stacks that are at those angles and then you measure things?
Yeah, we do it the old-fashioned way. We go hunt for it. So we sit on the surface and because we have this coarse motor that allows us to go explore large surfaces, we go and look, and whatever we find. However, if you really want to have some applications, you need to figure out how to do it in a controlled way. And we've recently, and the other groups, figured out a way to put graphene and put another layer of graphene and kind of control which way it goes. But one can never do it precisely at an atomic scale. So one may have to do it chemically. I don't know.
So the electrons that we're seeing graphene that are at the Dirac point, are we calling them massless fermions at that point? I guess I'm a little unclear on what's going on there.
We call them massless fermions everywhere, as long as the dispersion is linear, right? Where as long as the energy is proportional to momentum, they behave like relativistic particles. And their velocity is determined by the intrinsic property of the material, this Fermi velocity, and you can't change it. You accelerate the electron, it doesn't go, you apply a force on it, it doesn't go any faster. It just goes at its speed of light, which is the Fermi velocity. It doesn't slow down, it doesn't go faster, it just goes at its own speed, can't turn back.
I've got a question about the actual STM experiments. How did you see the graphene? I mean, you take a normal piece of graphite and you can do thousands of STM images atomically resolved, and you see only every other atom pattern. And in the Moiré patterns also you can see reasonably often. But how do you get the graphene?
It's an excellent question, and my colleague asked me that. So what happened? Well, we just find it. We're trying to figure out what's going on. We can measure locally the height, the separation between the graphene and the substrate. And now we know that in order to find those layers, we have to go to atomic steps. So let's say that you have an atomic step, and there's a piece of graphene that is draped on top of it. So there is a region where the distance is only 20% larger than the equilibrium distance in graphite. It turns out that is enough to entirely suppress tunneling between the layer, the coupling between the layers. So there's no more hybridization between the electronic wave functions. So this 20% is enough. And the way we find it, we just go hunt on the surface, we look at an atomic step, and then we zoom in and we check if it's triangular or honeycomb. If it's honeycomb, we continue. Then we look at the density of states. If it is linear, we put a magnetic field. But the bottom line is the magnetic field. Because if there's any amount of coupling to the substrate, those Landau levels are completely messed up, and we can actually tell how much it is coupled. So it is subtle. But on the other hand, there is no substrate that we know of at this point that shows as clearly the intrinsic properties of graphene. So it's worth the hunt.
Okay, so we are kind of a little over time at this point, so we're going to have to end the discussion at this point. So let's thank Eva. So I think I'll be turning